Nagapan Annamalai. He began his course of study at the Muhammad Satak School of Architecture Symposium. He then went on to pursue his higher education at Bharat Institute, where he also conducted his research Zonasa. He went on to conduct workshops at TCE Madurai on tsunami-resistant structures. He is currently heading an architecture and interiors consultancy, Kalpavriksha, since June 2014. He has had 8 years of experience in design, execution, and project management of architectural and interior projects. He has worked on many residential, commercial, hospitality, industrial projects in India and Singapore before setting up his own practice. He has also presented technical papers at various national level symposiums. He is also known to be a national champion at Archimen and Archimen Pro, India's biggest architectural quiz.
Welcome to the UGC lecture series on architecture. Building Services 3, Unit 1, Lecture 3. Air Conditioning, Basic Refrigeration Principles. The contents of this lecture is structured like this. We look at the types of cycles involved in the vapor compression cycle, like the condensate cycle, air cycle, chilled water cycle, and in the chilled water cycle we will be looking at how an air handling unit works. After which we will look at the cooling water cycle and the role of cooling towers in the cooling water cycle. And lastly, we will look at the various refrigerant control devices involved in the vapor compression cycle, and we will end up with the definition and the working principle of electric motors. Air cycle. Before air cycle we have the condensate cycle. The condensate cycle is nothing but it is similar to the vapor compression cycle, it is nothing special. So, that is why we moved on, we just skipped it and we are into the air cycle. In the air cycle, the refrigeration systems uses air as their refrigerant. So, in the previous lecture we saw the refrigerant liquid acts as a medium to cool the condition the space. Here in the air cycle, the air is used as a medium. So, here the air is compressed and expand to create a heating and cooling capacity. So, these were used on board ships and by food producers and retailers to provide cooling for their food stores in the past. Air is compressed and then heat removed. This air is then expanded to a lower temperature than before it was compressed, and work is taken out of the air by an expansion turbine which removes energy as the blades are driven round by the expanding air. So, basically air does the function of this refrigerant here in the air cycle. Next is the chilled water and cooling water cycle. Here this chilled water plays two roles. One is it helps in cooling the different spaces. It gets cooled first. In the first place, this water is chilled or cooled in a chiller where refrigerant is used as a medium to absorb the heat, thereby cooling the water. And thus this cooled water is circulated in tubes and into piping into various spaces, thereby cooling the different spaces. And the second part is water is used to cool the condenser. In the previous lecture we talked about water cooled condensers, the cooling tower, etc., where water absorbs the heat rejected by the condenser, then it goes to the cooling tower, it gets cooled and comes back and the cycle repeats. So, let us look in detail how this water as a cooling medium and water as used as cooling the condenser works. So, first the chilled water cycle. The chiller centralizes 3 heat exchanging cycles: the refrigeration cycle, the chilled water process and cooling water process. The chiller creates chilled water in a centralized building location that can be distributed for water usage and air conditioning purposes. The chiller is an all-in-one system that operates under the vapor compression cycle using refrigerants as the working fluid. So, what happens in a chilled water cycle? The chilled water loop transports water through the distribution network to supply the air handlers or air handling units, in other words, with cooling for air conditioning. So, this water first enters a chiller evaporator where the low pressure refrigerant is sprayed evenly over the surfaces of the tubes that contain the chilled water. So, the heat transfer process transfers the energy from the water to the refrigerant as the water passes through the evaporator. So, basically there is warm water which is going through the tubes or pipes. When the refrigerant is sprayed on top of it, the refrigerant absorbs the heat from the water, thereby cooling the water, and then this cold water is transported to different areas. So, after the water has travelled the length of the evaporator, the resulting chilled water is sent to designated destinations. The chilled water is distributed throughout the building via piping network leading to each tenant space. Chilled water piping is heavily insulated. As you know, when we transport chilled water, naturally the condensation happens when there is contact with external air and when there is a temperature difference between external and internal, and there is also a possibility of this condensate water affecting the other systems and leaking. Okay. So, to prevent that and to prevent external temperature to affect this chilled water, it is heavily insulated and it is covered with a vapor barrier which is impervious to moisture, which is very important. So, one or more air handlers serve each tenant depending on the capacity of cooling which they have to serve. An air handler is a sheet metal box that contains a fan and a cooling coil with aluminum fins bonded to the copper tubing to increase the heat transfer area. So, most chilled water air handlers contain a section called the mixing box, which is a sheet metal section with 2 openings in it. There is a duct connected to each opening and a damper located within each opening. Okay. The duct basically is to transport this supply air, return air to the space and get air from the space, and the damper is to open and close when there is no air supply or when there is some issues, like if there is a fire or whatever, this damper closes so that the air supply cuts off, thereby preventing the fire from spreading through the duct. So, damper plays the role of this closing and opening, and it prevents any transfer of fire or fumes or smoke. And one duct is used to bring return air from the conditioned space back to the air handler. The second duct is connected to the outdoors and is used to introduce outdoor air for ventilation purposes. So, naturally there is a circulation happening here. The air from the conditioned space is taken in to the air handling unit. There is also some supply of fresh air from the outdoor. These two are mixed and then sent into the conditioned space. So, the fan runs continuously, drawing a mix of outdoor air and return air through the air filters. So, the air filters basically they filter the airborne dust particles so that they do not enter the air conditioned space. The air is then cooled as it passes over the cold coils. So, as we saw earlier, the water which runs to the tubes, it is cooled by the refrigerant which is spread on top, and then this cooled water cools the air which comes into contact with these coils. This chilled water flow to the cooling coil is controlled by a motorized valve. Okay. So, there is a valve which controls the flow. So, whenever there is a requirement based on the cooling required, the valve controls the flow of water required to the space air handling unit. If the space temperature is at or below the set point of the thermostat, the motorized valve closes. So, basically they will have a thermostat which will sense or measure the temperature of the space which is to be air conditioned, and the occupants can set the thermostat to whatever required levels they want. So, based on this thermostat set point, when if the temperature is higher inside the space, then the cooled water is sent to cool the space. When it reaches the required temperature, the motorized valve shuts off the water supply. So, the thermostat is not satisfied, the motorized valve opens, causing chilled water to flow through the coil. So, this is a picture of a air handling unit, which is we saw it is a sheet metal box with mixing the coils and fan. Okay. So, this is the air handling unit. So, this is a simple layout of an air handling unit. So, here you can see the conditioned space. There is a space to keep the air handling unit. So, you might have seen in buildings and like office complexes or shopping malls, there is a space called AHU room which houses this sheet metal box. Okay. So, there is a connection between the conditioned space and this AHU room. One, there is a duct which goes from the air handling unit, which is supply air duct to the conditioned space. Then there is a return air duct. Usually these happen above the false ceiling, so that most of us might not have seen it. So, basically this is what happens there. There is a supply air duct to the conditioned space, and then there is a return air duct from the conditioned space, and then there is a input for some outside air, some fresh air. Okay. So, basically this is because if you keep on recirculating the same air, it becomes stale, and there is a possibility of causing some airborne diseases, the indoor air quality is not up to the mark. Okay. So, to compensate all those things, to improve the indoor air quality, you give us some supply of outside air, which is fresh air. So, let us look into the different components of a air handling unit in the following slides. The important components are the fans, ducts and dampers. Okay. So, these are the dampers, the one is highlighted in yellow, that is what I talked about. The dampers close and open depending on the requirement, and then this is the duct which takes a return air from the spaces. This is the opening or input for the outside air, and whatever air like if there is more air from outside and then from the return air and all those things, after filtration, then there is some relief air which goes out. Okay. Then after this outside air and return air is mixes, then they are supplied back to the spaces. Okay. They are cooled here and then sent to the spaces. So, here there is an additional component which is a filter. As I told earlier, the filter helps to filter the airborne dust particles, and lastly we have a heating coil. This is in a different case where you need in countries in cold countries where you need heating, you need to heat the space and not cool. You can use the same AHU, air handling unit, to do the process of heating, whereby you just need a heating coil. So, instead of the air passing through the cooling coils, it passes through a heating coil here and thereby supplies hot air to the space. And lastly, the one component here is a humidifier. So, as we know, if the air which comes from the inside, the return air, as well as the outside air, if there is not enough moisture content, you need to add some humidity to that. Okay. Otherwise, it will become very dry. So, they add another component called humidifier, which humidifies the air coming here and then supplies to the spaces. So, these are the basic components of an air handling unit. So, this is the chilled water cycle. Next, we are moving into the cooling water cycle. Here is a second water based system which uses a constant source of water to condense the refrigerant vapor called the condenser water. In the previous case, this chilled water was used to cool the air in the air handling unit and air condition the space eventually, but here water is used for a different purpose. Here the water is used to cool the condenser. We have already seen in the previous lecture that condensers can be air cooled and water cooled types. So, this cooling water cycle talks about this water cooled condenser type. So, the building maintains a cooling tower that is used to cool the condenser water and pumps that are used to circulate the water. In the vapor compression cycle, when the refrigerant runs through the condenser, heat is rejected from the refrigerant to heat a separate flow of water. So, whichever heat which is rejected from the condenser is absorbed by this water, and then this heated water is taken to the cooling tower to cool it. So, the heated water is sent to a cooling tower to be cooled. The refrigerant remains at the same pressure through the condenser, but exits at a lower temperature and then flows through an expansion valve that lowers the pressure of the refrigerant, causing it to evaporate. So, the last process we have already seen. So, here the next step is when the refrigerant evaporates, it draws heat from the warmer water in the evaporator, which cools the water. So, here they talk about this, in this particular step they talk about this chilled water cycle, where the refrigerant evaporates by drawing heat from the warm water in the evaporator, okay, thereby cooling the water and thereby cooling the space. The temperature of the cooling water rises in the condenser as a result of the heat transfer from the condensing refrigerant, and once the heated water exits the condenser, it is pumped to the cooling tower and the cycle repeats. So, let us look at the cooling tower, how it functions. In the cooling tower, the cooling water is sent down to the wet deck. The air is blown through the wet deck to evaporate a portion of the cooling water. The water that is not evaporated continues to flow down into the cold water basin, and additionally makeup water is added to replace the evaporated water, and all of the fluid is then sent back to the centralized utility plant for reprocessing. So, let us look at a sketch of a cooling tower. So, now we can correlate whatever I spoke just now, that water is sprayed, the hot water, you see the red color indicates the water is hot, from the condenser is taken to the cooling tower. From the top it is sprayed down, and there are different plates here like fins to break the water into small particles, and on the sides you have some louvers like aluminum louvers or metal louvers, which allows the air to circulate. It induces a draft of air. So, and there is a fan, propeller fan, which keeps rotating and removing the moisture from the air. So, thereby evaporation happens. So, after whatever water is evaporated, the remaining water which comes down is collected in the sump. It is already cooled by now, and then this cooled water is once again sent back to the condenser to do the process of cooling the condenser. This is how the cooling tower works. The principle in which the cooling tower works is called the counterflow principle. The counterflow principle is used in cooling towers. Here the water falls downwards and the louvers serve to break the water into droplets that are easier to cool. So, upward air flows in, airflow is provided by fans that can be cycled during cold weather to maintain proper water temperature. So, cooling towers normally drop the water temperature about 10 degrees. This is how the cooling tower works. This is the principle. This is an image showing a cooling tower used in large scale buildings. Next we will look at the different refrigerant control devices. So, there are several different types of refrigerant control devices, but they all serve to control the amount of liquid refrigerant entering the evaporator. So, basically that is the role they play. They control the amount of refrigerant, liquid refrigerant entering the evaporator. This is the primary purpose. The type of control used in a system depends upon the application. So, for different applications we use different systems. Shown here are 4 most popular types. The first is a metering device, or it is fitted at the expansion valve. So, the role of the meter is, the meters correct the amount of refrigerant to the evaporator. So, the quantity, the correct amount, it is installed in the liquid line at the inlet of the evaporator. So, it is somewhere here. Common devices are automatic expansion valve, thermostatic expansion valve and fixed bore like a capillary tube. So, this same expansion valve as a metering device, and it is used to maintain a pressure difference between the high pressure side, which is the condenser side, and the low pressure side, which is the evaporator side. One of the types of the expansion valves is thermostatic expansion valve. So, the purpose of a thermostatic expansion valve is it maintains a constant evaporator superheat. If the evaporator superheat is high, the valve will open, and superheat ensures that no liquid refrigerant leaves the evaporator. So, this is the role of a thermostatic expansion valve. Next is a similar device called a capillary tube metering device. So, here this metering device controls the refrigerant flow by pressure drop across it, and the diameter and length of the tube determines the flow at a given pressure. So, depending on the length of the tube, the pressure is maintained, and it does not maintain evaporator pressure or superheat, it does not do it, and there are no moving parts to wear out. And lastly, we will look at the solenoid valve. It is also one of the types of valve which controls the flow of refrigerant. The solenoid valve is used to stop the flow of refrigerant within the system. So, it controls the flow of refrigerant to multiple sections of evaporator, and it is also used to prevent the refrigerant from migrating through the system when the compressor is shut off. So, basically the solenoid valve opens up the refrigerant. So, when the compressor is shut off and the system is not on, the solenoid valve is closed, thereby the refrigerant does not move to the evaporator. Next we will be looking at the electric motor. So, we have looked at all these components in the vapor compression cycle, like the condenser, compressor, evaporator, expansion device, the receiver, everything. But to operate, to make it function, you need an electric motor. It is a very simple basic electric motor which helps in operating this compressor. So, let us see the basic working principle of an electric motor. So, it is a current carrying coil in a magnetic field, and it experiences a turning effect. So, this is a schematic diagram. N represents north pole, S is south pole. So, there are 2 poles of a magnet, and the coil in the center is connected to a power supply, variable power supply, and when it is in the magnetic field it rotates, it experiences a turning effect. So, when a current carrying conductor, that is a metal coil, is placed in a magnetic field, there is an interaction between the magnetic field produced by the current and the permanent field, which leads to a force being experienced by the conductor. So, there is a magnetic field between these 2 magnets, there is a permanent field here, and it leads to a force which in turn rotates the conductor. The magnitude of force on the conductor depends on the magnitude of current which it carries. So, it is quite obvious. The force is a maximum when the current flows perpendicular, as in figure A, and it is 0 when it flows parallel to the field, as in figure B. So, this is a schematic diagram which shows the motion of a current carrying loop in a magnetic field. As I already explained, it represents the north pole of a magnet, represents south pole of a magnet, and this is the conductor or the metal coil. It is connected to brushes, and then the brushes are connected to a power supply. Okay. And once the current power supply is given, it rotates in the magnetic field. So, let us look at the different parts of a motor. Armature or rotor, which is here. Next is the commutator, which is fixed to this rotor. Next is the brushes, which is fixed to the commutator. Next is the axle, which helps in keeping the armature in place, and lastly it is the field magnets, which are on either sides, which creates a magnetic field. So, now let us go into detail of the different components like the armature. The armature is an electromagnet made by coiling thin wire around 2 or more poles of a metal core. So, it is nothing but a thin wire which is wound on a metal core. The armature has an axle and the commutator is attached to the axle. So, this is the black one is the axle, and the green semicircles or arcs are the commutators. So, when you run electricity into this electromagnet, it creates a magnetic field in the armature, and that attracts and repels the magnet at the stator. So, once you pass electricity, the magnetic field in the armature, there is some magnetic field which attracts and repels. So, there are two opposite poles which attracts and repels. So, thereby the armature spins through 180 degrees. To keep it spinning, you have to change the poles of the electromagnet. It has to be constantly changed, otherwise it will not spin. Next is the commutator and the brushes. The commutator is simply a pair of plates attached to the axle. So, here you can see the commutator, the green arcs, which are pair of plates attached to the axle. These plates provide the two connections for the coil of the electromagnet. So, they provide the connections, basically they are connected to the electromagnet. The commutator and brushes work together to let the current flow and also to flip the direction that the electrons are flowing at just the right moment. So, the contacts of the commutator are attached to the axle of the electromagnet. So, they spin with the magnet. So, they play two roles. One is to rotate, to keep the electromagnet in rotation, and also to flip the direction of the electrons. Okay. The contacts of the commutator are attached to the axle. If you are here, the commutator is connected to the axle, which is the center portion. So, they spin with the magnet. The brushes are just two pieces of springy metal or carbon that makes contact with the contacts of the commutator. Those are the brushes. So, this shows a actual picture of a motor, a simple motor, where you can see this electromagnet. The thin coils are wound around the metal piece, and then you can see the casing, the metal axle. In addition to the main components described earlier, let us look at all the control devices needed for the normal operation of a system. We will see how these devices operate under normal conditions. When the system is off, the refrigerant is waiting in the condenser. For it to enter the evaporator, the solenoid valve must first open. The signal to open the valve comes from the room thermostat, which makes a contact with the valve when the room temperature is higher than the set by the occupants. Some systems have a timer which puts off the system when the building is unoccupied. Others have an outside thermostat that prevents the refrigerant system to switch on when the outside temperature is too cold. So, the compressor will only start when the timer and outside thermostat allows it to do so. The liquid refrigerant starts to flow towards the expansion valve. At this point, it is at high pressure. You can see the refrigerant flowing through the side glass. As it flows through, the refrigerant is filtered to remove the possible residues or metal particles. The liquid refrigerant at high pressure thus arrives at the expansion valve, which is set to lower the pressure to obtain the temperature required in the evaporator. The expansion valve is also a flow control valve. It controls the amount of refrigerant entering the evaporator depending on the evaporation rate. The evaporation rate varies with the amount of air to be cooled, the air temperature and the degree of humidity in the air as it passes through the evaporator. The expansion valve measures the evaporation rate by means of a bulb located at the evaporator. This bulb measures the amount of superheat of refrigerant. When the degrees of superheat increases, it means that the refrigerant is evaporating faster than it enters the evaporator. The expansion valve then opens more to increase the flow. However, the number of degrees of superheat drop. It means the evaporation is flooded with liquid refrigerant. The expansion valve will then reduce the flow until superheat returns to the desired range, usually 8 to 12 Fahrenheit for thermostatic expansion valves, or electronic valves operate with a superheat range of 4 to 6 degree Fahrenheit. You will notice that the expansion valve also receives a pressure signal, also measured at the evaporator outlet. This allows the expansion valve to adjust to the pressure drop in the refrigerant as it goes through the evaporator. The pressure drop lowers the evaporation temperature slightly and could give a false superheat reading if it were not compensated for. Under normal working conditions, the level of refrigerant stabilizes in the evaporator so that the flow of liquid is proportional to the amount of heat to be absorbed. The compressor starts up at the same time as the solenoid valve opens. The compressor startup is also regulated by a pressure control that measures the minimum pressure needed to be present at the compressor suction inlet. This is the cut-in pressure. This pressure is usually reached when the compressor starts up because the remaining refrigerant in the evaporator has evaporated while the compressor was off. This control is useful to prevent the compressor from starting when there is not enough refrigerant coming into the compressor from the evaporator. The compressor can be shut off from one of the three following controls. The first is a room thermostat. This thermostat shuts off the compressor if the ambient temperature is lower than the set point temperature. The second is the pressure control that measures the minimum required pressure at the suction inlet. This means if too little refrigerant is coming from the evaporator, the compressor will be stopped. This is the cutoff pressure. The third is the pressure control that measures the pressure at the discharge outlet. It is called the high pressure cutout. When the discharge pressure is too high, the compressor shuts down. This may indicate that there is an operating problem that could damage the mechanical components. Under normal operating conditions, the compressor runs as long as the thermostat has not reached the desired room temperature. The gaseous refrigerant which is drawn in from the evaporator is compressed to a high pressure. The refrigerant temperature then rises instantly with the increase in pressure, and refrigerant flows towards the condenser. In order to try to adapt to the variable flow of the refrigerant arriving at the compressor, some systems use multiple compressors. As the flow of refrigerant increases, the suction pressure increases, which in turn allows a larger number of compressors to start up. The condenser receives the gaseous refrigerant at high pressure and high temperature from the compressor. The function of the condenser is to condense the refrigerant in order to return it to the evaporator. The compressor and condenser fans operate simultaneously. It is the outside air that absorbs the condensation heat. The function of the inverted U trap located at the condenser inlet is to reduce the hammer effect caused by the sudden arrival of massive refrigerant in the condenser. This usually occurs when the compressor starts up. The inverted U trap also holds back the liquid refrigerant and prevents it from returning to the compressor when the compressor is off. The refrigerant reaches the bottom of the condenser as a liquid at high pressure and high temperature. As soon as this happens, it again passes through the expansion valve to re-enter the evaporator at the required temperature and pressure. The refrigeration cycle continues to operate as long as the room thermostat indicates that there is a need for cooling. So, with this we come to the end of this lecture. In this lecture we dealt with the different cycles in a vapor compression system, like the condensate cycle, the air cycle, chilled water cycle, in which we saw the detailed explanation of what is the air handling unit, how it works. We also saw about the cooling water cycle, and the role of a cooling tower and a cooling water cycle. Then we looked at the different types of refrigerant control devices available, and lastly we saw an explanation of the working principle of electric motor and its components. So, the question for this lecture can be like this: explain the workflow of a chilled water cycle with a diagram. What are air handling units? Describe in detail about cooling water cycle and the function of cooling towers. Explain about any two types of refrigerant control devices. Explain the working principle of an electric motor function with a brief description of the parts of the motor. Thank you.